Hi everybody. I finally finished a project after 2 years. This is my solar powered trail camera that has been the bane of my existence for 2 full years, but today it's finally finished. 2 years ago, one of my friends spotted a mountain lion on her property and I wanted to get a photo of it if it was possible. So my first thought was using those hunter trail cameras that they use that are battery operated. But I didn't want to go out every few weeks and replace the batteries, so I went to solar power next. I had no idea how difficult this would be. This is going to be a technical description about this particular project. So if you're technically minded, this is the video for you. If you're not, I'll link a non-technical description in the description below. So that's the place for you. I built this on a Raspberry Pi. Raspberry Pi Zero. They're about this big. They are unbelievably powerful and unbelievably cheap. So if you haven't played around with these things, you really should think about it. Another reason I was working on this, why I wanted to make it solar, is that I have a few other ideas for outdoor implementation for computer projects. So that might be a wind vane, that might be a precipitation sensor of some sort. If I want to leave something on a farmer's field for 2 years, I want that to be able to run autonomously without me checking in with it every day or every 3 months. And this project will allow me to reuse what I've learned for solar electrical infrastructure to power the next project. I was also inspired by James Balog's documentary Chasing Ice, where he puts cameras that look just like this out north of the Arctic Circle to track the recession of glacial ice year to year. It's a really cool documentary, and I kind of copied his design with the pelican case and the huge batteries inside. Okay, let's have a look at the actual enclosure itself. This is a pelican case. This is the 1450. The reason I chose a pelican case and not like a Tupperware of some sort is this very important release nozzle right here. This will allow pressure to change within the box itself as pressures change outside. Now normally, if there is that pressure differential between a Tupperware, let's say, and the outdoor environment, you get condensation. This will remain completely dry within the enclosure as a result of this little nozzle, as long as the rest of the box is completely sealed. That brings me to this little window here that looks absolutely terrible. This is silicone caulk up here. It will bear temperatures from -60 to all the way to 400 degrees Fahrenheit. Obviously, our natural environment, it'll never see those temperatures, but it is encouraging. It's also very flexible, so it'll allow for the expansion and contraction of two different types of plastics here. I had a lot of problems with that, so silicone caulk is the way to go with that. We'll go down here as well. This is where our solar power comes in. This utilizes a marine waterproof connection. So this will screw in, and it's completely waterproof as well as airtight. And it also uses the same silicone caulk that we just pointed out above. Also on the exterior, we notice this is our passive infrared sensor. We'll talk more about that in a second. But basically, whenever you wave your hand in front of it, you'll notice it's taking a photo as we do that. When we take a look at this thing, there's lots of cords and wires and stuff. It's really not that complicated. This is all of the electrical infrastructure. You'll notice this is an enormous battery to power something that's about this big, which seems crazy, but is necessary. This is our solar lithium battery. This charge is all controlled by our solar controller up here. This is the kind of the brains of the electrical side of the house. So as our solar panel power comes in, it goes to the solar controller, which diverts energy to our battery. And then if we have enough power from the battery, the solar controller will send that through the load to our 5-volt voltage drop, which ultimately will go to the Raspberry Pi here, which I would call the real brains of the operation. So the way this works, there's movement in front of the trail camera. It's caught by the passive infrared sensor. That goes back to this circuit board and triggers a message to our Raspberry Pi. The Raspberry Pi lights an LED, our flash, as well as takes a photo. This is stored on our hard drive, and then once a day it's uploaded to AWS. A few lessons I learned through this whole process. First is don't bother going out and doing your own solar thing and buying each piece piecemeal. Do your best to just find a kit on Amazon that'll suit your needs and just buy that. I had the hardest time finding a battery that worked independent of the solar panel and a solar controller. Just buy a kit, find everything that works, and trust the manufacturer to do that. The second thing would probably be backing everything up on the cloud. I should have known that, but I cracked my first hard drive and totally ruined all of my progress. So back everything up in the cloud. Number 3 would be notating somewhere the operating systems of Raspberry Pi that you're using. Because this project took me so long, there were, I think, 2 major updates to Raspberry Pi OS, which broke the camera module. So I found myself reverting and trying to understand which Raspberry Pi image would allow me to use that camera module. It was a real headache. I wish I had just written it down in the first place. And number 4, the final thing, I had the hardest time getting cron jobs to work on reboot, especially when power isn't always consistent. I don't know why this continued to break, but I converted one of my reboot cron jobs to a System D service or a System CTL service. That has worked perfectly. Again, I don't know why it's happened, but I had the hardest time getting cron to work upon reboot. That's the whole project. Thanks a lot. I hope you liked it. I had a blast creating it. And stay tuned for my next solar-powered Raspberry Pi project.